Good afternoon to everyone. My name is Jorge Luis de Franco Jr., and I will be talking about my project 4. I'll be building different models and I'll be analyzing the willingness of an applicant to either pay a loan or to default on a loan. As mentioned before, I'll be building different models, including a decision tree, a logistic regression model, and a neural network model to predict the probability of a loan default. This is my table of content, and I will be talking about all of this here. This is my data dictionary. So I have provided to you guys all of my variables and all of their meanings. And you guys could take a look here and pay attention to their meanings. Okay, so the first thing that I'm going to be doing in order to start my project is to split the data. So I have split the data into a training and into a validation data set. There was no need to test the data set because my sample size is small. I have used JMP in order to split my data, and I had to create a column where the initialized data was random and where the random indicator is equal to a 75% to 25% split. And you guys can see that here. I have also labeled my values. 0 is equal to training and 1 is equal to the validation data set. So after that, I have decided to split the data. I then eliminate some variables. So basically, I have conducted a descriptive analysis on the training data set in evaluating bivariate relationship. And this analysis was done in each variable and have helped me to eliminate some variables. So over here, I have the column contributions for both the partition, which is the decision tree, and the column contributions for the logistic model. So based on these contributions, I have looked to portions that are not significant to my overall project. And I have found that Reason, Mortdo, CLNO, that I found that they were not significant to my overall project, to my data set. And this was also supported by the fit y by x function in evaluating bivariate relationships. And I just want to make sure that you guys understand that the reason in which I have decided to delete these variables are that they don't have importance to the project, to the overall project. So it's definitely okay to delete them because they will not change my final response and they will not have an impact to my models. So I ran some multicollinearity as well to see if there were any multicollinearity between the variables. And as you guys can see, I didn't find no multicollinearity between these variables. Values were really good. The maximum that I found was a 21%, similar 35%, but that's really okay. So as you guys can see, I did not find any multicollinearity. I did not find any problem with multicollinearity. So I was eventually ready to start my models and to discuss about them. So after deleting my variables, I had decided to do a multicollinearity test to see if there are any multicollinearity between the variables. I did not find any multicollinearity in this problem, so I was ready to start my models. The first model that we are going to be talking is a decision tree. I have chosen to include only 8 splits in this decision tree since it's much better to visualize, it's much better to visualization. And If I were to present this to someone, I wouldn't like to have like 148 crease, making it difficult to present and to visualize that. So we are going to be talking about a decision tree. The misclassification rate for my decision tree is at 0.39 for my training and 0.38 for my validation. The split history, as mentioned, will give the value of R squared as a function of number of splits for both the training and the validation. So basically, the split history stops as it reaches the maximum value of the validation dataset. We can see that both the training and the validation are close to 0.40, and the R square number keeps increasing as we keep splitting the data. So I'm going to also be checking the column contribution, which I have already provided that to you guys earlier. And in order to do that, I'll be using a full tree. And eventually, I will discard job, Yoj, and link, since they don't have any contribution to my overall model. The overall measure of model accuracy for the classification model is the misclassification rate. The misclassification rate for the validation in the dataset is equal to 10.74%. The four classifications rate are represented by the confusion matrix, in which we are going to be taking a look now. According to the confusion matrix, the model is better at predicting if applicants paid loans than if applicants defaulted on a loan. And this could be found since the rate of correctly predicting a 1 equals to 197 plus the sum of this, and the rate of correctly predicting a 0 equals to 1133 divided of the sum of this. So we have the correctly predicting if applicants paid loans equals to 94.18%, and if applicants defaulted on a loan equal to 68.64%. We can also take a look at the leaf report, and we can see that there are branches in the trees that have a much higher concentration than the average of 68.64%. And you guys could take a look here and see that there are branches much higher than 68%, as mentioned before. Okay, so we can also talk about sensitivity and specificity. So sensitivity is the true positive, while 1 minus specificity is the false positive rate. Our model, according to the ROC curve, should be considered better than random. Lift curve. This is also really important, and we can see that our model is 4.5 times more likely to present to get a yes with 10% of the data, and our model is also 3.8% times more likely to get a yes at 20% of the data. For a no, I was not provide great values here, so it made it hard to capture the data. Now I'm going to be talking about my second model, which is the logistic regression model. So variables that are most significant in predicting the probability are the length, depthing, and the ROG. You guys could go back to the data dictionary and take a look on their meanings. I have decided to use them because they are most significant according to the column contribution, as you guys can see, and most variables also pass the p-value test, and they may be a good fit for the performance. Again, we are going to be removing value, Yoj, and loan since they don't show to have a great contribution to the overall project. This is the misclassification rate for my final logistic model. And we can also see that our model is better at predicting if applicants paid a loan than if applicants defaulted on a loan. And as mentioned before, you guys could do that by doing 821 divided by 823 and 18 divided by the sum of this. Lift curve. So our model is 5.5 times more likely to get a yes with 10% of the data, and our model is also 3 times more likely to get a yes with 20% of the data, as you guys can see here. Additional measures of accuracy can be used when building this model, and they are sensitivity and specificity. Sensitivity is true, while 1 minus specificity is the false positive rate, and our model according to the ROC curve should be considered better than random. Now I'm going to be talking about my third model, which is the neural network. I have my confusion matrix raw counts, I have percentages, and I have also the misclassification rate. I'm not going to go into further details because I have already discussed this with you guys. But according to the confusion matrix, my model is also better at predicting a no than a yes. And we could find this by looking at the rate of correctly predicting a yes and the rate of correctly predicting a no. Additional measures of accuracy are both the sensitivity and 1 minus specificity. Sensitivity is true, while 1 minus specificity is the false positive rate. Our model, according to the ROC curve, should be considered better than random. The lift curve showed that our model is 5 times more likely to get a yes with 10% of the data and 3 times more likely to get a yes with 20% of the data. For a no, I wasn't provided great values, so it was hard for me to capture the data. Okay, so now I'm going to be talking more about the structure of the neural network. So we have the F shape on the three nodes that are represented function. We have our input layout represented by blue, where the number of nodes is equal to the number of independent variables and are represented by bad. We can see there's a line correcting each independent variable to each of these three nodes, and these inputs are basically used to create the outputs coming out of the nodes. So there's a weight assigned to each independent variables, and as you guys can see here, basically this means that age 1 get a 2.17 weight, age 2 gets a 2.00 weight, and that's the intercept number. And we also have the information about either the bad is equal to 0 or 1, and by watching this code, which is provided by SAS, we can eventually see how things are connected by their weight. Okay, so basically in the neural network, we could use three nodes on my second layout as well. And I'm just going to run this again to show that to you guys. And by doing this, I have realized that my R square value was higher on the validation and lower in the misclassification rate. And I will be also providing the diagram and the SAS code when running three nodes on my second layout. And it's also important to mention that when I ran three nodes on my second layout, uh, my yes rate increased to 37.3%, which is represented by 1. Okay, so now I'm showing that to you guys. You guys could see that my diagram changed. Now I have my independent variables and two hidden layouts on my input logger, and every independent variable is connected to the first layout, and each node in the first layout is connected to each node in the second layout. And then we have our final function coming in the input, which is represented by bed. So I'm using my SAS code to provide further explanation, and you guys can see that right now we have three nodes represented by their weights, which the first node gets negative 3.79, second 5.20, the third minus 7.25, and plus the intercept, which is negative 4.77. And then we also have the final layout and eventually the calculations of the probability represented. Okay, so one important thing about the neural network is to have access to the prediction profile and then eventually be able to play around to see probabilities based on playing around with the variables, as you guys can see here. And also, this can be found in JMP. So I have the summary report of my variables importance rate, and you guys can see that the most important are debting, the link, and the rug. Okay, so now we'll be talking about, I'll be comparing my models. So I'll be deciding which model is better and why. So in order to do this, I have saved the predicted formulas for the logistic, for the decision tree, and for my neural network model. And eventually, I have realized which model is better and why. I have used JMP to decide my best model. And in order to do this, JMP pretty much looks for the model that has the highest R square. And as we can see here, the partition, the decision tree, was my best model. And I have concluded that the decision tree was my best model based on the R square as mentioned. And let's talk more about the decision tree. The decision tree is a decision support that uses a tree like a model of decision and their possible consequences that enables you to make a decision about some kind of process. So as we could see, just to make sure that I say this again, I have included 8 splits on my decision tree, and I have included my column contribution again here so you guys could see. So basically, based on my project, the variables that play the most importance on my data are debit to income ratio, number of delinquent credit lines, and they are characterized by debiting and the link. So what does that mean? So it simple means that the willingness of an applicant to either pay or default a loan is related to their debit to income ratio and their number of delinquent credit lines. We are going to go back here, and this is represented by debiting and the link. Go back. So this information is extremely helpful because when we do these types of analysis, we could see the major contributions to, in this example, let's say, willingness of an applicant to either pay a loan or to default on a loan. And let's just take a look on the confusion matrix again, just to make sure that you guys can understand the model. So we of course we are going to be looking at the validation, and the model is better at predicting if applicants paid loans, which is characterized by 0, than if applicants defaulted on a loan, which is characterized by 1. So let's look again in the percentage. I just want to make sure that you guys understand this because this is extremely important. So again, where did I take the 68.64% and the 95.18%? Okay, so uh, when the model is predicting if applicants paid a loan, we are looking to the 0 portion of the confusion matrix. So we are looking 1,133 divided by 1,133 plus 70 plus the sum of this, which is 94.18%. So again, when the model is predicting if applicant paid loans, we are looking at a 94.18% interval. And when we are looking to if applicant defaulted on a loan, which is the 1, we are looking to 68% because that's based on 197 divided by the sum of these values represented by 1. So this is the conclusion of the project. I believe that this information can be extremely helpful to analysts uh, looking through the column contribution, looking to the confusion matrix, looking to the, let's go back a little bit, looking to the misclassification rate for the problem, the split history, looking the column contribution as mentioned, leaf report, sensitivity. Okay, so all of this helps a lot when we are doing our analysis. So it's extremely important for us to pay attention in each one of this, the leaf curve, which is extremely important as well. And this is the conclusion of the project. I hope that you guys have enjoyed. I hope that you guys can extract a lot of information based on these models. I hope that you guys have paid attention to the model comparison as well to determine which model is better. And I hope that you guys have enjoyed this project. So I'm going to end this presentation. I'm open to answer any questions, and it was definitely a great time to talk to you guys about this project and about these models in general.